Let me show you how to be a good Bayesian.
In today's episode, I am thrilled to welcome Sean Pinkney, a managing director at Omnicom Media Group and a STAN core contributor. With a background spanning mathematics, economics, and statistics, Sean shares how he transitioned from economics to data science and how his work evolved into advanced Bayesian modeling. We dive deep into his zero-sum normal project in STAN, exploring why he created it, how it improves the efficiency of hierarchical models, and what its broader applications might be. We're also joined by a special guest star, Adrian Seyboldt. You may remember Adrian from episode 74 of the show. If you don't, well, I recommend you to listen to his dedicated episode. It is in the show notes. And Adrian will provide additional insights into the technical and philosophical, even, aspects of flexible parameterization and population effects. So whether you're a fan of Bayesian stats, of STAN, or simply curious about innovation in statistical modeling, this episode is packed with technical gems and big picture reflections alike. This is Learning Bayesian Statistics, episode 133, recorded February 11, 2025.
Let me show you how to be a good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations. What's a Bayesian? It's someone who cares about evidence.
Welcome to Learning Bayesian Statistics, a podcast about Bayesian inference, the methods, the projects, and the people who make it possible. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country. For any info about the show, learnbayesstats.com is la place to be. Show notes, becoming a corporate sponsor, unlocking Bayesian merch, supporting the show on Patreon, everything is in there. That's learnbayesstats.com. If you're interested in one-on-one mentorship, online courses, or statistical consulting, feel free to reach out and book a call at topmate.io/Alex_Andorra. See you around, folks, and best Bayesian wishes to you all. And if today's discussion sparked ideas for your business, well, our team at PyMC Labs can help bring them to life. Check us out at pymc-labs.com. Sean Pinkney, welcome to Learning Bayesian Statistics.
Hello, great to be here.
Yeah, that's awesome to have you here. It's been a long time coming. We met finally at StanCon 2024 in Oxford, and that's when I learned that you were one of the main persons working behind adding the zero-sum constraint to STAN. So, of course, we're gonna talk a lot about that today. We may have a surprise guest at some point, we'll see, to talk about that precisely. But first, can you tell us what you're doing nowadays, Sean, and how you ended up working on this?
Yeah. On the zero something, it'll be a pretty, I think, hopefully funny story, interesting as well, because basically I wasn't focused on this at all. So I find it kind of great that you're interested in it, and I got into it a bit accidentally, but we'll get there. So just a bit about me. So currently I am working at this big company called Omnicom Media Group. So it's a big advertising agency, which is kind of different than I think a lot of the folks that come on here. I am a STAN developer. And we can kind of get into how that even became, because right now I'm not actually doing so much like statistics and math. I'm a managing director, so I moved up in the company, so I'm leading a lot of projects, and it's a lot more business type stuff. Now, I love STAN and I love Bayesian statistics, and so I keep up with it. And Bob Carpenter, who has been on here before, he's like, that's so cool that this is like your hobby. And I just, now I start telling people that, okay, this is like my hobby, Bayesian statistics.
Yeah. And when actually did you discover about Bayesian stats? Were you introduced to Bayesian stats first? Because, Sure, you define that as a hobby, but you do a lot of stuff around Stan, and often your projects are not small ones, so it takes time. So yeah, I'm curious, how did you get introduced to that, and why that sticked with you?
Yeah, so actually, let me just like go back a little bit. So my background, so I majored in economics and math when I was in undergraduate at the University of Colorado in Boulder. So yeah, I grew up in Colorado. That's my kind of hometown. Currently, I'm in the DC area, and I actually wanted to be an economist. So I was one of these weird people who knew what they wanted to do, like right when they went into undergraduate. So right off the bat, I double majored in econ and math. And I kind of like basically planned out the whole 4 years about what classes I needed to take in order for that to get all done. Um, and so I knew I was going to go to grad school, and the plan had been okay to get like a PhD in economics. Um, I also, was really interested in like cycling and triathlon, and so I was on the triathlon team at Boulder, and I've done a bunch of those. And for a while there, it was like, okay, so I was balancing these things of, doing these academics, but then also training quite a lot. At that time, I was probably training like 20, 25 hours a week. Um, it was like, I just can't believe how fast I was back in the day now that feel like an old man. um, but yeah, so then I was kind of like, I wanted to try that stuff out too. Unfortunately, I had like a really bad accident senior year of college on the bike, and I needed to get a bunch of things fixed. So like knocked some teeth out, broke my jaw, and I took a year off between undergrad and grad school, and I worked actually worked for a geologist up in North Dakota, weirdly, like 12-hour days. I was working all night long. And we were up there and we were looking at the cuttings that were coming up from drilling rigs, like wells. So they would drill and these cuttings would come up. And we would log them, and we would say, okay, and we would look at like the radiation, we would describe the appearance, the color, we'd test if there was like any oil and stuff. Um, and it was kind of neat. And I made pretty decent money, so I was able to basically save up because I was just living on the site there. And then at that time, the place in North Dakota was really cheap. It was like right at the beginning of like this boom. And so I was able to like rent like like an apartment for like something like $150 a month or something ridiculous, whenever I was up there. And then I got into grad school at University of British Columbia, at that point, and this was for economics. I was like, hey, I think I don't know if I'm gonna like do a PhD. I don't know if I'm gonna go 5 full years. Let me do this, and it was great. So I went up there. It was a 1 year program, Canadian University, was able to pay for everything. And I did apply to some PhD programs. I did get in at the end. And at the same time, I met my wife, my only, my wife. But at the time, I met her, and I was like, do I want to go to a PhD program? And I'm sure that this relationship will stop, because it was nowhere near where she was, or I could move to where she was. So I decided to move to where she was. So that kind of ended my a lot of like that academic trajectory. Now the financial crisis happened at that same time, so 2008, 2009. Had a really tough time getting any jobs, and I kept hearing back though, funny enough, that they wanted more statistics, and they were like, "Wow, you have like econ and this stuff," but I really had no statistics. Like I had a probability course, so in undergrad at that time, like back in the early like 2000s, they didn't there wasn't like data science wasn't really a thing yet. A lot of these tools that we take kind of almost for granted today just weren't developed at all. And so, yeah, I had like one probability class, and then I had whatever the probability stuff in econometrics. And I was like, you know what? I guess I'm just gonna go back to school because there were no jobs. I have family in Ohio, so I applied to this university called University of Akron, quite like a local college university. But I have family there. They gave me full funding for a master's degree in statistics, and I was like, all right, let me try this. Let me take 2 years and do statistics. Now it was all frequentist. I remember one of the professors there even like disparagingly like was like Bayesian, like what do those people know? At that point, I didn't really know much about anything Bayesian. Um, but that was like my first like real like deep dive into statistics, and then I went into actuary, and I did some actuary stuff in Cleveland for about 6 years, and then I moved over to media, and we're finally going to get to where the Bayesian stuff comes in. So I got this job at this company called ComScore. There was someone who had written some stand stuff, and I was like, wow. I started to look at it, and I was like, this is super interesting. Um, and as I was starting to read more about it and what it can do, I realized that this is like what I've been looking for, like my whole like I don't know, like as I was looking at analytic stuff, I always wanted to build the model that I wanted to build, and I didn't want to have to rely upon some package or like, you know, I think for like a number of years it was always like, oh, how can I like take these packages and this thing and like fit it to like the model that I have and like all the different nuances that you have with your data. And now I felt, oh, okay, I didn't have to worry about the sample. I didn't have to worry about all these other things, and I could just focus on building the model. Um, and so that was about 2017. I think I even asked some questions on the forum. Asked some questions to Bob. He was grateful enough to, give me a lot of pointers, like he still does with people on the forums. And then I just spent a couple years just building a bunch of different stand models, and just getting very familiar with Bayesian modeling, and all like the different gotchas, and reading as much literature as I could. Um, and I started to then answer a bunch of questions on the forums. And I started to really like everyone, and I just felt very welcomed in the community. Um, and so I felt like at a certain point, I was like, you know what? I know enough about this that I can, I think, give back to it. So I started to add some like small functions into Stan, and that sort of got me in with more of the Stan developers and talking with them, and just like what else could we do? What issues do we have? How can we make these things faster? Um, and that's really kind of how it spiraled out. Now, in my professional life, I went from like managing, so I went from like an individual contributor to managing like a data science team while I was at ComScore, and I was doing quite a lot of data science. So we did like vectorization uh, of clickstream. So a clickstream is all these panelists, so people who've agreed to have like their web browsing, tracked, and you can see like, okay, they went to page 1, 2, 3, or whatever, and you can take that as a corpus, and you can like vectorize it. So now, with LLMs, it's like almost commonplace. But this was back in like 2017, 2018, and like Word2Vec was just coming out, and it was like, wow. And then, we had like this whole new area that we're exploring with it. So it was really cool. So we were doing, there was a lot of machine learning, a lot of bespoke modeling, um, and it was really fun atmosphere to be in at the time. Unfortunately, that company isn't doing that well, or it's kind of like been on life support for a while. and I didn't feel like I had like a great trajectory there, with how things were going for the company as a whole. Even though I loved it, I loved all the people I worked with. So I started looking elsewhere, and I kind of stumbled upon this role at my current job. And now I've been here about 3 years, and I do some analytics, but yeah, it's mostly like project stuff. And in that time, um, I've still wanted to contribute to Stan, and I feel like if anything, it's gotten much more researchy and technical, and less, there's applied components to it, but I think more about the tooling anymore, and just making it better, and better for people who are using Stan, but hopefully better for people who are using PyMC, or who are using any probabilistic programming language at the moment.
Yeah, thanks for this extensive background. I didn't know that's how you started with Stan. That's really interesting. That's really similar to how I started with PyMC, actually. Lurking in the discourse, answering questions, bothering people with questions. So,
I mean, we all have to start somewhere, right?
Yeah, exactly. And since we didn't start with like math degree or stats degree, well, we had to find another way, a way around. Yeah, and that's really interesting, because then like all the stuff you did has always been very, very core to Stan. So that's why I think it's super interesting to have you on the show today. And I'm also not surprised that Bob helped you a lot, because yeah, he's just incredible. Like very, very generous person with his time, and also very good, like pedagogically. I think he's a very good explainer of very complex topics, even though he's himself very technical. So yeah, like it's something I really appreciate in Bob and in most of the Stan team, I have to say.
Yeah, I think just a side on that, the documentation that was really mostly Bob was like very instrumental in having the Stan documentation like so extensive. Was a key reason why I just found it. It was like getting like another degree, like reading through the Stan manual basically, and I think people still reference it as like, okay, go look at the Stan manual and you can see what this like distribution of this transform or whatever. So I mean, it is really that good.
Yeah, no, for sure. And so let's turn to one of your big projects, actually, and the main one why I wanted to have you on the show today, which is let's call that the zero-sum normal project. So zero-sum normal is how we called it on the PyMC side, and that project is dear to me because I worked a lot on it with Adrian Seyboldt, actually, who agreed to join us today to talk about that, because I know like Adrian is really the father of that stuff on the PyMC side. Me, I was just applying his vision under his supervision. So yeah, he agreed to come on the show today. So to talk with us. So Adrian, welcome back to the show.
Hey.
Thank you so much for being with us today. For listeners on the show, long-time listeners, they will recognize you from episode 74. This is in the show notes. You were here to talk to us about NumPy, which is your implementation of HMC in Rust, and also we talked about zero-sum normal, which is something we're going to talk about right now with Sean. So I know Sean and you, I think you know each other from StanCon, but if you don't, well...
met that.
Yeah.
Okay, perfect. So yeah, let's dive in. So Sean, can you tell us basically what that zero-sum constraint that you implemented in Stan is about? And yeah, like maybe first giving us an elevator pitch for that, why that's useful and when.
So, okay, I'm gonna like go back a little bit because it's really funny how it came to be in Stan. So basically, like Bob, he said, so he asked Brian Ward, who's one of the Stan developers. He's like, okay, he's like, I really want the sum to zero vector like in Stan. And so there was a PR that was opened by Brian, and it was like that naive one where you just like sum all the elements and take the subtraction of it as like the last element. And I saw this PR and I was like, oh my god, no, like this is not good. We don't want that way of doing it in Stan, and there are some reasons for that, and that I think Adrian, you and we can probably talk about here in a second. But I had been working actually with Bob and Seth Axon and Meenal and some other people on the simplex transform paper, which is like at this point 3 years in the making. I don't know. We got to finish it. So it's like basically done. I think there's just a few things, and we should just put it up on archive. But one of the transformations that we're using in that paper actually was derived from this like thing called the inverse ILR transformation, which is done in compositional data analysis, where they do a bunch of stuff with like simplexes, and everything is like modeled on this like compositional data, which it has like this denominator, and so it's constrained within this area. Now, the way that came about was, hey, they wanted this thing called an isometry in the coordinate space of the simplex. To get that, you basically need to and I don't know the correct necessarily term, but like orthogonalize. We need some orthogonal sort of transformation. And when you look at it, it's the same thing as doing like a zero-sum contrast transformation, basically. And so in the intermediate step of that, you actually get out a zero-sum, which is pretty neat. And it's actually a really nice parameterization of a simplex, which I think we're going to put into Stan sometime soon. But then I was like, Bob, Brian, like this thing is so much better. Now the issue that we had was that the way we had coded it up was like very inefficient. So it was like you would create this like big matrix, like Helmert, contrast matrix, and then you would like multiply it, which when you're doing that thousands of times in HMC is like super inefficient. And so we start looking at it, and I think Seth, he's like, oh, okay, I can actually take out all the matrix stuff and just make it vectors. And then Brian starts to look at this, and he's like, oh, actually, like we can just do one loop. We don't even have to create these vectors. And so let's just do like one loop. And so that's what it came to be now in Stan. So it's like very efficient. It's just one loop, and you have this thing. Now, in the same time period, right? I think, Adrian, maybe this was even at StanCon, but it was like, oh, PyMC has this already. And so then after we like developed this whole method, I'm like, okay, like let's see what PyMC is doing. And I'm like, okay, so like it's different, but at the same time, it ends up being the exact same thing. And so
just a different orthogonal transformation, basically.
Because any orthogonal one will work. But I think the one neat thing that you have is it's very easy to go into like multi-dimensional tensors and to make each like in PyMC, right?
Yeah, that was kind of that just fell out of the implementation.
Yeah.
At the beginning, I didn't think about that. I just implemented the one-dimensional case, and then I was thinking, wait a second, that's I can just do that in a loop. Let's do that.
And I really, and so I started, so our implementation, it's not quite as easy to generalize to that, but I did work out for the matrix case, and it's just one loop, it's like, one loop through the matrix, which is really nice, so you don't have like a double or anything, and it's so it's fairly low complexity.
Actually, is the PyMC implementation, I think that might iterate twice through the array or something. I'm not actually sure.
I think it does, because in the PyMC one, it like has to sum through all the elements like in that call or whatever in that dimension, and then it goes through again, and it like, I don't know, it does a subtraction and everything. However, you can do it not exactly the way that you have it, but the way that I've done it, and you can do it so it just goes through it once.
That's
now,
cool.
yeah, and you can actually generalize it to multidimensional tensors. It started to like hurt my head, like to even look at the matrix version. And like I use like SymPy to like look at what like the matrix equation looks like, and I was like, oh my god! And I was telling Bob how like, oh, this is so cool, like. And then if you have like another tensor, it'll just like add these other things, and he's like, oh, this is like a Ramajuan, like like the way that like you know how long the equations were and everything. But yeah, I think we'll just do the matrix version next instead, because we don't really have anything that's like more than a matrix. There's no as like a constraint, and so it would be like a bigger project to add that.
Yeah, there's another generalization that kind of I think I coded some really horrible code for one project once that didn't really end up being used, but that I would really like is kind of for rect arrays. If you kind of have an array of predictors and you want to sum it to 0, but the number of elements is different each time.
Oh, yes.
So if you have that, maybe you could kind of get the tensor version based on that then. But doing that efficiently was a lot harder, because then I think it wasn't in the end it wasn't as efficient as the nice clean one, but still not horrible. So that's something on that we might want to add on the PyMC side. That would be cool as well.
Yeah, I have so actually this is so funny. I'm working on a case study with Mitzi Morris. She actually did like 99% of the work. She was just like, oh, let's like, I want to do this like sum to 0, so like I'll put your name on it basically. But she's really done most of it. But in it, she's doing like an ICAR model, and in it, they have different like a ragged array basically. But in Stan, they don't have ragged arrays, so you just make like one big vector. Mm-hmm. And then, you slice it, and then you go through and you use the transform to get the zero sum from it, and it actually like works pretty well, because then you're literally only going through, because it's just a loop, and the loop you only have to go through it once.
Yeah, I think there are actually quite a few different related things that might be nice for different applications. For instance, you could also have constraints where you say, I want A times my vector to be 0. So you just want the subspace that's defined by the kernel of something. Or you want A times B greater than B, than C, some other constant, and have some convex shapes or something. So I guess there's a lot of space to experiment there and to come up with cool things. And then I guess the applications would come up at some later point. I think that would just happen naturally.
Yeah, actually, like in the simplex version, where we're using that ILR transformation, which is basically the same thing as our sum to 0, and then you do like a softmax transform, and because everything is like very nicely uniform from like the sum to 0, it just like really samples nicely. But I'm doing like I have it's on this chalkboard I'm pointing over here, but I worked out the doubly stochastic version of that like really nice transform using like the ILR and like everything, and it's super cool, and I'm like, I can't wait to put that in. Now doubly stochastic, I don't know how many times people would even use this. Like I think I've used that like once, possibly ever. But the thing that I'm super interested in is I think it can be generalized to a matrix where you want the sum, a rectangular matrix. So a doubly stochastic matrix has to be square. But if we want a rectangular matrix and we want the rows and the columns to have a certain sum, and then we know what the total of the matrix is as well, I think it can generalize to something like that. Which in my line of work, there's some cool stuff with that, where you might know some stuff about the population, and you might have some information about a sample, but you actually don't know what the population like internal values of the matrix are. But you know what the totals of the columns and the rows are.
So can you make? I don't get it yet.
Yeah. like, let's say, actually, one of the things that I've seen, like in the application, is like with voting. And so you might have a bunch of voters, I don't know, some state, let's say Florida, and you might have a bunch of information about some of their demographics. So let's just say you have race information and age information, but you don't have the cross between race and age.
Ah, okay. I think I get now what you're
Yeah,
getting at.
and so you know how many people of these races voted this way, and you know how many people of certain ages voted this way, but you don't know that table, the marginals of race by age. But if we have this nice constraint and we know the totals, we can use Bayesian methods to then sample likely values. We can have like a stochastic value matrix here, and it's like super neat. But you really need to have a nice transform, in place, and so you're not just like doing
because
like
otherwise
normal,
the sampler will probably die pretty fast, right?
Exactly. Yeah, especially like with really big. So that's like the thing I've been like kind of working through, and trying to get.
Yeah, that
But
sounds
yeah,
cool.
it's totally related. I think there's so many things with like the sum to zero that we can do, and I know, Alex, you had asked me at StanCon. You were like, what if we have a new group?
Right.
And immediately I go back to this forum post where like Michael Betancourt's talking about, no, you can't generalize. You can't generalize with sum to zero. Now, okay, here's the thing. All right, so I did some homework, Alex.
Okay.
So this is my attempt. I did some homework, and I'm super interested to hear your guys' thoughts on it. And
so wait, let me set the context for listeners, because most of them were not at StanCon. So basically so first, folks, for those who really don't know about the zero-sum normal and the zero-sum constraint, really I recommend listening to Adrian's episode, because we go into details about why and how you would use that, and the strength and the weaknesses. But the short version is you would use that mainly when you have, let's say, categorical covariates in your regression. So, for instance, like in the Radon example that everybody knows from Andrew's paper, you have homes. And so if you have a global intercept in that model, for instance, which would be the mean of the homes, then if you partially pull the coefficients on the homes, you are going to have to use a zero-sum constraint on the parameters of the home. Otherwise, you have an over parameterization, because you're estimating two intercepts in a way. So you would have this parameter in there that's pm.zero-sum normal, dims equals home. But then my question to Sean, and that's because it's a question I often have, I often work on, whether for elections or other purposes, is like, what if you have, so homes here, we often call that groups, like if you use BRMS or Bambi, that's what they call that, they're group, so that's one group. My question was, what if you have a new element of that group? So the group is known, and you've inferred the population parameters of that group, but you observe a new home. How do you handle that? Because then there's zero-sum normal constraint is not is not observed in the test set, because now the mean changes because there is a new element. So yeah, that's the context. And so apparently, Sean, you've done some homework about that, so thank you. And I'm also very curious to hear about what Adrian's thinking is about that. So yeah, first let's hear from you, Sean.
Yeah. Okay. So the distribution. So okay, we take our zero sum, and we say that if we assume normality, so it only works with normal. I think. Okay. Good.
At least that's. I also only know how to do it with a normal. If it's not normal. Okay.
So maybe, I don't know. Yeah, maybe there's some clever ways to do it with something that's like normal-ish, but or closed under some of the normal properties of like addition and all that. But anyway, like normally, right? Often when we do hierarchical models, we do have this like normal property of these like random effects and fixed effects and everything. So it's nice because of that. And when you look at the distribution of the zero sum and you estimate what that covariance matrix is, it's like it's got this diagonal property, and then it has all the off diagonals have like a negative covariance. And what we can actually see from all of this is that using like I'm like, oh, I just like want to get into all the math, but I feel like if you're listening to this, it would be super annoying. So I'm just going to try to like say it in a general way, which is you can take the property and what you've estimated, and you can actually like back out what like the population like mean effect is, or the variance of the population mean. So the variance of your mu, your intercept, or your fixed effect in the zero sum case will be much smaller when you use a zero sum. Like the variance of that mu will be much smaller, all right, than if you just had a regular hierarchical model. Now, the really cool thing though is that with a zero sum thing, the estimates that you get on the mean of mu are actually typically much better often, and you get higher ESS and all these things. Like the HMC is able to sample from the zero sum often much easier than the non one. And so you can actually go back and you can get the population standard deviation, and you can generalize out, because we're going to know, we can back out like what the covariance and take those effects into account. And then we could say, oh, if we had a new group, this is how all of the other effects would change in the zero sum, because anyway, there's a way that you can like look at all the addition, like what you add to it, and then the new one, but it's just going to be based off the prior and what you've estimated from your sample. So it's not going to be like, maybe there's some clever way to include like some information about how large that group is, or some other standard deviation effects, but right now I just like looked at it from, okay, if you use your posterior of what you have in your prior, and then this information about the multivariate normal that's implied by the zero sum, then I think, yeah, you can do it, which is very long-winded. But I don't know, Adrian, I want to hear, maybe you have a cleaner way, because I like literally just worked on this for, over the last day or two, and so it's a bit new in my mind.
Yeah, what I really is kind of oh, sorry, yeah, go ahead.
Yeah, no, just Adrian, if you, like, just to tell you guys, if you feel like when I share your screen, because it's going to be easier to explain, you can do that, right? Like, especially now on the YouTube episodes, we had the video, so people, if they want, they can refer to that. So yeah, if that's helpful to your explanation at some point, sure, feel free to do that. You should be able to share your screen. And now, Adrian, yeah, back to you. So if I understood correctly, Sean, what you said, it's mainly, well, you cannot directly, of course, have information about that new home, for instance, but you learned about the population parameters, so you can use those in your predictions. And, well, if you had better priors about that new home in particular, then definitely use those prior in conjunction with what you learned about the population, and that you can make a prediction based on that.
And how like the zero sum constraint, like how that manifests into the model, and it's almost like you're backing out that effect and then applying this new group, and then you can like reapply it, and then you could rederive everything.
Yeah, I think what cleared up my thinking around that a little bit was seeing what happens if kind of really distinguishing between effects relative to the population mean and effects relative to the sample mean. So if I have an infinite population of homes, or a population that I assume is infinite, and I have a sample of 50 homes from that population, then I can ask, is the radon level or whatever level 50% higher than the average among the homes that I observed, or is it 50% higher than the average of all the homes that there are? Kind of one is relative to the population, the other is relative to the sample. And if I don't use a zero-sum normal in my model, I can always compute both, right? I can just say, okay, I've got my posterior, and I can take the home-specific value and just subtract the mean of all the observed homes in that draw. then I get back kind of the zero-sum effects kind of relative to the population of homes that are observed. So the relative to the sample of homes that are observed. And sometimes, kind of depending on the application, sometimes you might want to look at one, and sometimes you might want to look at the other, right? Maybe I'm interested in how much more radiation is there than the average home, or I might be interested in how much more radiation is there compared to the homes that I observed. Especially kind of if the population I'm looking at actually isn't infinite, like, I don't know, US states or something. It doesn't really make much sense to ask, is that value in that state higher than some infinite population of US states? I mean, there are only that many.
Yeah, I mean, actually, that just like that's a great. I love that, like the difference between the sample and the population. Yeah, if I think of alpha as like our random effect, and if you take the mean, and so that would be the random effect by group. So you might have k groups, whatever. If you take the mean of it in the zero sum case, that mean is going to be 0, right? Like, by construction. But in the case of just like a traditional hierarchical model, it will be non-zero, and you'll have some non-zero variant. And so I think like that is kind of the key, right? Like that, like you have this average effect, and then we can use that to sort of back everything out. But it's actually really neat. And Alex, I just want to thank you for bringing that up at StanCon, because I think it is quite neat. I don't know. Do you guys have anything written up on this?
You're asking the wrong person for a nice written up.
Yeah.
Unfortunately, I don't.
I know.
We did a bit of that.
Like, we should write up.
Yeah.
But kind of to get back to how you can then get back the population effects is kind of if you start with your model that counts everything relative to the population, so the infinite population of homes, then it turns out you can just distinguish that in the model itself. So you can take a normal distribution with mean mu and so some fixed mean, and you can just decompose that into a zero-sum normal and a normal distribution for the sample mean. So you have a scalar distribution that's the sample mean of the population, of the sample, not the population. And you have a zero-sum normal that tells you what's the distance to that sample mean. And then kind of if you write it down, then you have kind of a scalar value with a normal distribution, and you have plus the zero-sum normal, plus the normal distribution from your intercept. And then you can marginalize intercept plus that thing. And then you can kind of turn a normal hierarchical model into just strictly a reparameterization of a zero-sum normal. And you can then kind of take the zero-sum normal and go back the other way and try to kind of undo the marginalization manually after sampling, which is really annoying to do. So I'm usually too bored, or not. I usually don't, to be honest, but it's definitely possible. And if you add more layers, it gets more involved. So less fun, but.
Yeah, it would be nice to have like an automatic way to just do this, because I mean the zero sum, it does, at least in my test, like it does sample often, almost like 95% of the time better than just like the regular hierarchical model. So you're going to get better estimates, and then when you do all the backing out, of course, like it translates to all of that.
I would definitely really like to have a library that you can just tell, here my effects. Code that as a zero-sum normal, but give me back a trace object that includes not just the zero-sum effects, but all the population effects as well. So you have access to both, and you can look at whatever you're actually interested in your application, but the sampler sees whatever's better for the sampler. So that would be really nice to have, but I don't think that exists at the moment.
No. And we started...
Next project for NutPy.
Yeah. And we started doing a bit of that, Adrian and I don't know, a year ago or something like that, where we have a proof of concept, but we never cleaned it up,
no.
We never cleaned that up. And also it's because, like, it gets, like, if we want to put that into PyMC, it has to deal with all the different models people can have. And then if you have a lot of zero-sum normals in there, that's like really hard to track everything down. So I think the stuff we had was already quite complete in the sense that it was like main effect for A, main effect for B, and interaction of A and B, and then how do you recover the population means, because you have zero-sum normals everywhere in this model. But like people can make arbitrarily complicated model in PIMC, so then it's very hard to generalize. But yeah, that would definitely be a very, very valuable contribution. I know Luciano Paz did a lot of work on that with a client at PIMC Labs, but I don't know how generalizable that stuff is. So yeah, like that's something we should probably ask Luciano what he thinks about that.
Maybe
yeah.
we need 3 or 4 non-generalizable implementations, and then at some point we can extrapolate an actual implementation that works in at least most cases. But
yeah, exactly. But for sure, it's the good thing. I mean, the silver lining though is that I think if you you can still get a decent prediction, at least in my experience, if you take the population parameters that you learned at inference time and then have a more informed prior for your new members of the existing groups. So you can still get, even though mathematically it's not the best that you could have, because the best would be to do what we just talked about, that's a practical solution that's not too hard, and that at least is accessible to most people right now. So yeah, don't despair, folks. Like even if we can't do that right now, like you still can have decent predictions for new members of existing groups without being completely doomed.
Yeah. So actually, on that point, like the transformer, because I went through, you can another way that possibly I think that you could do that is if you unconstrain, like if you do the unconstraining transform of your estimated zero-sum vector. And so now you'll have like k minus 1 elements, right? And then you add a new one. Well, like you just randomly draw a normal 0, 1 or whatever it is that your kind of prior on the unconstrained scale would be. And then you just go back and in the case, I think for us, it would be you just add that whatever you drew from the normal 0, 1 divided by the square root of like k plus 1 times k plus 2. And then the last element would be the minus of that.
But I think that's still missing something, because we still need to then we are adding that variance in a sense. So we were saying the variance from the sample mean, we are adding it back there. But that variance is kind of absorbed in the intercept term now.
So yeah, this would
so
just
we kind
be
of actually need to take out the variance out of the intercept term. So we can't just add the variance, we also need to remove it at the other end, right?
Yeah, but there might be a way where you can use like I don't know, that unconstraining transform, and then it would be much simpler in my mind, because it's just like, oh, I just have this function, it would apply all the stuff, and then it would come out. Anyway, I'd have to think about it more.
Yeah, story of my models. So we only have 15 minutes left, I think, before Sean has to leave. So we can switch gears now. Adrian, you can leave if you want, but I think you're gonna like the next topic. So do whatever you want. Again, thank you so much for popping in and talking about that stuff. That's it's always very interesting to me to get back to where are we right now on our thinking on that topic. But next, what I'd like to talk about with you, Sean, is the flexible Cholesky parameterization you've recently written about in a preprint, and I think that's also what your StanCon presentation was about. So if you can like tell us a bit more about that. What are the practical takeaways? What are the strengths and weaknesses? And I'm guessing that if Adrian sticks around, since he heard about Cholesky, he'll have questions.
That definitely sounds interesting, but I haven't. Now it gets out that I didn't actually listen to your talk at Stanford. I think I was preparing something for my talk.
There is a YouTube video. I felt so bad because I ended up missing I think like a half day of talks just because I ended up like working on my presentation and on some other things for StanCon. But I did get your talk, so you should feel bad, Adrian. I think it's fine. So actually, yeah. So this thing has been like probably like 4 years ago, thinking about Cholesky parameterizations and doing some stuff. And there was someone on the forum who wanted just all positive correlation matrix. And I was like, oh, okay, well, just take, instead of like a hyperbolic tangent where you transform the raw parameters to -1 to 1, just have it be like exponential, just have it 0 to 1 or whatever. And that works, like you do get all positive, but it doesn't give you uniformity over the space of positive correlation matrices. And that's because this other guy, Enzo, who was also at StanCon, he messaged me because he saw that post, and then he noticed this issue with it, and I was like, all right. So then I said, okay, that's interesting. Let me think about it. So I go off and I think about it for a little bit, and I read like a bunch of different papers, and I'm like, okay, I'm like looking, and I start to see that there's some commonalities, and I start to piece this thing together, and that's where this preprint came about. And you can actually see like how there are these bounds that have to be applied, and if you apply them such that you do the Jacobian adjustment for the bound, that's just the Jacobian. Like that's all you need. You just have to sample from that bound, and that will preserve like the correlation matrix. And it works really well for positive correlation matrices. And when we compared it to rejection sampling, you can see that it does uniformly sample over the space of positive correlation matrices. And what is very interesting about that is in the Cholesky formulation, if you see like it's a lower triangular matrix, and these things like each row ends up being somewhat like of a dot product of like the previous elements of the other row in order to get the full matrix. And what the reason why the original time when I did that, I just constrained it to be positive, the raw scale, that doesn't work, is because if you multiply two negative numbers together, you can still get a positive. So there's a space, right? There's a space of these vectors, like the dot products of those vectors, such that they can actually be negative. Some of the elements can be negative, but they have to be negative in a very special way, such that that when they multiply together, that it ends up being positive. And that was basically like the density that we were like missing from that other piece. And so this came about, and then recently I'm working with a few other people. I show how you can actually put block structure into your matrix with this way. So not only does it allow bounds, but it allows you to put in specific known values or specific constraints, such that, hey, this correlation has to be equal to this one, and stuff like that. So now instead of having k choose 2 or n choose 2 free parameters for a correlation matrix, you'll have n choose 2 minus whatever those restrictions are, which in this guy's case, it's actually really nice because it like halves the number of free parameters, and he gets
correlation matrices, they have so many parameters so quickly. It's
kind of a nightmare. And so we're working through that, and then recently there was some other people I've been talking to, and we're gonna look at some other like ways of making these parameterizations hopefully better. But that will be out soon. So the block structure, I mean, you can, like, that paper, it allows it. The paper was super short. It's like 3 pages long on arXiv. So I think most people didn't understand what the hell I was talking about or what it was supposed to be doing. They thought, oh, it's just like bounds on this. But those bounds are really key, and they're key to actually putting in like all this structure. There is an issue that I do want to mention, and I do mention it in the paper. There's a section about an issue with it, which is that you need to. So the bounds can sometimes just not work. They can be unenforceable. So that means you would get a divergence. So how would that come about? So let's say you put a certain restriction. So in the case where there's no restriction, it will always work. But in the case where there are restrictions, you might have some restrictions that if you didn't take into account that restriction, like way up ahead at the very top of the matrix, so like if you have a restriction way down, and you're just sampling, okay, and it doesn't know about it, and then all of a sudden it gets to it, and it says, oh, there's not enough space left to make this restriction happen. So in the case of like all negative correlation matrices, that space is actually smaller than all positive, and it's much harder to sample from that. And so you can see, like, if you constrain everything to be negative, you'll get tons of divergences, especially if you put like an LKJ that's like really small, like 1 or 2. And so if the elements, if they get big enough, if you draw something such that it's like a negative 0.9, there's like almost nothing left. And so it's like, oh no, in order to have any space left, this next parameter has to be drawn such that it's positive. But then we're saying that the bounds must be negative. And so it says, okay, well, that's incompatible, and you'll get a divergence.
That reminds me a little bit of kind of trying to sample from convex spaces, like a polygon, for instance, where you always also run into issues like that. So kind of, for instance, there definitely exists a bijection from r squared to a square, but actually writing down one, even if especially if it's not really a square but something else, is actually surprisingly hard. And I never managed one that doesn't involve an ODE somehow.
And I mean, it basically is the same, because you're looking at like these intersections of of this like conic section with the unit sphere, and you're trying to make sure, like, okay, like I want to make sure that I'm within that. But yeah, you have to either do some crazy look ahead, and right now I've derived a 1 look ahead, but really you would need the n look ahead. You would need to look ahead to every single element, make sure that you have all the correct bounds, but then it would update, so you'd always be looking ahead, right? Because you would, once you draw a parameter, that updates what all the bounds can be. Mm-hmm. But now that you've had restrictions, like I don't know, it gets like super complicated.
Is that actually a special case of a convex subset of? So I guess we can just say we have vector space r to the n, and say, okay, some convex subspace of that. So we have some matrix A, and I guess so we want all x such that A times x greater than B. I think, no, that doesn't cover covariance matrices yet, because I think there we need something quadratic, right? Because we need positive definite. But it's still a convex space, at least, I think.
Yes, I think so.
It's funny how that keeps coming up. That's kind of within the last 2 or 3 weeks, I don't know, several times in completely different contexts.
Yeah, there's I don't know, like this guy who's talking to me now, he's talking about sampling eigenvalues such that like your sample eigenvalue, like you have a prior, so you can take your sample and you can get eigenvalues, and then you would actually put a prior such that your correlation or covariance matrix would like have very similar eigenvalues. And he's like sort of worked it out, but then there's still a case where like the largest and smallest are like way different than what it should be. So like there's some fundamental issue there.
Yeah,
But I think
especially
there's a
kind
lot.
of eigenvectors, for instance, are also an issue, right? Because they kind of
Well, there's like an indeterminacy
same
for
issue as
HMC, right?
happens when you want to sample an angle, that it's you want to sample in some manifold that's not diffeomorphic to our usual space, to the Euclidean space, because the topology is different, and that also happens with eigenvectors, for instance. Yeah.
Yeah, there's I mean, yeah, I think if you were doing like Riemannian, like Hamiltonian Monte Carlo, and like I'm sure that there's like ways to efficiently sample a lot of these. But yeah, if we want to use it in our implementation of HMC, where we need this diffeomorphism between Euclidean space and the space of positive definite matrices with ones on the diagonal, I don't know. Maybe.
I guess the problem is sometimes that diffeomorphism just doesn't exist, right? That's just fundamentally.
Well,
I mean, for
it doesn't exist.
covariance
Right, so you have
matrices or correlation matrices, it does exist. But
You have to
for
do charts.
eigenvectors,
then, right?
it doesn't.
Yeah, so then you have to like figure out certain charts, like spaces of it, and then just like, okay, I'm gonna like just have it just be this chart of that space. So it won't be the full space, but yeah, I think like orthogonal matrices have the same thing because there's like an indeterminacy with like the sign, and so you have to just like set it to typically positive, right?
Nice. Damn. Super fascinating. Thanks, guys. Like, I drank your comments. I think I understand 50% of them though, which is already good. Yeah, if I understood correctly, we don't have that constraint already ready to use in PIMC, Adrian. Do
You
we?
have LKJ Cholesky? No.
We have, we do have LKJ Cholesky, but I think the one you set up that's like only positive, I don't think we have that.
I don't know about that.
Out of the box. Yeah.
But you have a Cholesky factor that you can sample uniformly? Oh, okay.
Yes.
Actually, I'm not. So we definitely have a Cholesky covariance thing. I'm not actually sure if we ever implemented the correlation one.
No. Yeah, I mean, I think so. You mean LKJ core?
Yeah.
We have that, but I think it's wrong for some reason. So we tell people not to
only
use
the
it.
bad one that kind of does rejection sampling if you run into the border or something. But
I think so. Yeah. So
the
we
covariance
definitely tell
one is
people
properly defined. Yeah. But
yes. Yeah. So like we always use LKJ cov decomposition, and then you get back the correlation matrix also with that for sure. But we don't use LKJ core because there's an issue in there. So
there's
should change that maybe.
There's a guy who was doing a bunch of stuff in Stan, and then I think he did some stuff in TensorFlow probability. His name's Adam Haber, and he implemented in TensorFlow probability the construction of the Cholesky factor of correlation matrices. Is quite clever, and I like went through it actually the other week to figure out why this works, and I figured out that it's actually a stereographic transform from the positive pole of the sphere. Okay, so what what is done there, and it's super efficient. Like we should put this into Stan, you should put this in PyMC. So when you sample the unit vectors, so the Cholesky factor of correlation matrices, each row is a unit vector, and on the diagonal must be positive. So that's where this like stereographic thing comes from. So if you do a stereographic projection and you have it as 1, so that would be the diagonal value of. So let's take one of the vectors. It would be a 1. And then you do a unit vector of normals. So basically you just take standard normals, and then you do the norm of that vector with the 1 here. Well, that will get you exactly what you need for this. and it like works really well, and it's super fast and super efficient. And yeah, if you work it all out, it comes to be the stereographic transform from the positive pole of the sphere, which is like, and I was like, oh man, this is so cool. And yeah, without even having like the derivatives or anything, if I just like code it as like a function in Stan without like the C++, it's like oftentimes more efficient than the built-in one. And it's way better numerically, because it doesn't have this issue with the stick breaking process where you get to like a very small number, right? And you get like problems around 0. And so it doesn't have that. And so it samples way better from like an LKJ of 1.
That's cool.
Because of it.
Is that just in TensorFlow probability itself? Is that in the package, or is that somewhere else?
I don't know. Anyway, like I can put some. I'm not sure where it is, but Adam was the one. He was the one who like told me about it and was like, "This is how I implemented it." And then I just.
That sounds cool.
I don't know. Did it in
I mean,
Stan.
I couldn't follow completely, but it sounds cool.
I mean, I can give you like, I don't know if you can follow like the standard, but I can give you like just like the function that I use for it, and you can kind of see how it all works. I could probably even have like ChatGPT show like how it goes from stereographic transform to this, and like you can see the connection there. That took quite a bit to figure out exactly what's going on. But I was like, how can this work if you're setting the last element to 1? Like, I was just like, that like blew my mind. And the reason why is because there is a pinch. So we were talking about all this geometry of these spaces. And there is a pinch that like, there's just something fundamentally. You can't sample from this like, this value. Same with a unit vector. You need to like push everything away from 0, right? Because there's like a singularity there. But if you set that singularity, then everything samples great. So
Nice, yeah. I mean, for sure, if you have like, so if that's in TFP, definitely we should link to that in the show notes. Or if you have any public link to share with us, I'll put that in the show notes. And yeah, in any case, the function you were talking about, for sure, we're curious about that, because like if we can add that to PyMC and that helps, for sure that would be great. Yeah, for sure. Damn.
nice.
Thanks, Sean. Super cool. So I had so many more questions for you, but I know you got to drop. So like, actually, let's call that a show. Unless before I ask you the last 2 questions, is there any other topic you wanted to talk about or mention and that we didn't get to yet?
I mean, maybe you can just have me on again. We'll do more topics that way. Yeah. This has been great.
Awesome, great. Okay, so let's close that up, and before that, of course, I'll ask you the last 2 questions I ask every guest at the end of the show. So first one, if you had unlimited time and resources, which problem would you try to solve?
This is such a hard question. And like always, like I feel like the pithy answer is that, why are we here? What's the Douglas Adams, like what's the answer to the universe? Like the fundamental question. Because I feel like everything from that question, like once you kind of have an idea of what the meaning, right, of life is, you can really focus on fixing all these other problems. So, climate change, wars, all that stuff. But, if we had a really, really good answer, I think that would be something. If we could understand it, if it wasn't completely incomprehensible, that's what I would spend all my time trying to figure out.
What do you do if there is no meaning?
I don't know. Global warming. Poverty, war, like just make people so like they're not, hurting.
Yeah. Second question: if you could have dinner with any great scientific mind, dead, alive, or fictional, who would it be?
I feel like, this was also a hard question. I was like, man, how, who is like someone that would be just fun to be around, because there are people who are super smart, but I wouldn't necessarily want to have like dinner or a beer with them, right? Like they're really cool. So I came up with Da Vinci. Just he has done so many interesting things. I have no idea how he, figured all this stuff out. How he was so driven to come up and to just study so many different areas. Would love to talk with him and have some wine and,
So how's your
just
Italian?
understand the process. My Italian's terrible. He's got to learn English. He could probably do that in like, a few days.
Yeah, but, I mean, that sounds like a nice dinner for sure. Like, I would definitely do the dinner in Italy, so, like, you might want to work on your Italian. Awesome. Well, great. Sean, that was absolutely awesome to have you here. Learned so much. I'm going to listen to that episode quite a lot when editing, because there's a lot of stuff I've missed, but I will make sure to ask you questions. Adrian, thank you so much for taking the time. That was awesome.
Thank you.
You're a great co-host, so like, if you want to change careers, like, please let me know. That was great to have you both on the show. You're both welcome anytime. And thanks again, Sean and Adrian, for taking the time and being on this show.
Thank you, Alex. See you guys.
This has been another episode of Learning Bayesian Statistics. Be sure to rate, review, and follow the show on your favorite podcatcher, and visit learnbayesstats.com for more resources about today's topics, as well as access to more episodes to help you reach true Bayesian state of mind. That's learnbayesstats.com. Our theme music is Good Bayesian by Baba Brinkman, feat. MC Loss and Mega Ran. Check out his awesome work at bababrinkman.com. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country. You can support the show and unlock exclusive benefits by visiting patreon.com/learnbayesstats. Thank you so much for listening and for your support. You're truly a
good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations. Let me show you how to be a good Bayesian. Change calculations after taking fresh data in. Those predictions that your brain is making, let's get them on a solid foundation.